This lesson is about the derivative. It is one of the fundamental, maybe the fundamental idea of all of calculus. It's going to take what we just learned with limits and apply it to some ideas that you learned back in algebra and come up with this concept of a derivative. The idea of a derivative is that you want to find how fast a graph is moving at an instant, at a point, at a specific point. A nonlinear graph specifically. If you have a curve that's going up and down and you want to know exactly its rate of change, its slope at a point, that idea is the derivative. You get the derivative starting with two separate points. If I wanted to know the slope at this point down here, x1, y1, I would start with another point close by, x2, y2, a close point. Imagine you're zoomed in on this graph, so these points are pretty close together. And I would take the slope of the secant line from the first point to the second point. Difference of the y's over difference of the x's. And then I would take a smaller secant line. The slope of a secant line that's a little bit where the x's are a little closer. So a secant line from here. Then a secant line even closer, and a secant line even closer. The idea is, as these secant lines, as the x values of the points you're taking the secant line from get closer and closer together, this secant line essentially becomes the same as the tangent line. And the slope of a tangent line at a point is the same as the slope of the graph at a point, and that is called the derivative. The idea of the derivative comes from limits because you're essentially taking the limit of the slope of these secant lines as the x values become closer and closer together. And I'm going to give you a demonstration here. So here you have a function and you have point P. If you want to find the derivative of the function at point P, the slope of the tangent line at point P, the first thing we want to do is create a second point. So we're going to show you point Q, also on that curve. Now we want to draw a secant line through point P and Q, points P and Q. So there's your secant line. Now we want to let Q get closer and closer to P, so that this secant line, the points on the secant line get closer and closer together. So as you see, the slope of that secant line is getting closer and closer. And it keeps going closer and closer. And as I let it touch, pretty much, as P and Q get infinitely close together, whereas the distance between P and Q becomes 0, this secant line between P and Q essentially becomes the tangent line. And the slope of that line is the derivative. The derivative at a point. The slope of a function at a specific point. The process of finding the derivative of a function is called differentiation. If a function has a derivative, it is said to be differentiable. So these are just two vocabulary words you're going to need to know. If a problem tells you to differentiate a function, it's telling you to find the derivative of a function. If a problem asks, is this function differentiable at x equals 5? It wants to know if the function has a derivative at x equals 5. So you have this graph here. You have 2 points, x, f of x, and x plus delta x. Some small number, some change in x. So this is a little bit over there. So this is x plus delta x. I'm delta x over from x, the change in x over from x. And this is f of x plus delta x. In order to find the slope of a secant line, you would take the difference of the y's, f of x plus delta x minus f of x, divide that by the difference of the x's, x plus delta x minus x. In order to find the slope of the tangent line, you would take the limit as this delta x approaches 0, as the distance between these two x values goes to 0, as this comes closer and closer, like we did in that last little diagram with p and q. So the limit as delta x approaches 0 of f of x plus delta x minus f of x over x plus delta x minus x. This is the limit definition of a derivative. We can simplify this a little bit. The numerator f of x plus delta x minus f of x, you can't simplify that. But the denominator x plus delta x minus x, you see these x's change, or cancel, so all you're left with is delta x in the denominator. And that makes sense, since the denominator is only the difference in the x's, and that's what delta x was, the difference of the x's, what you added to get to that second x value. This right here, f of x plus delta x over minus f of x over delta x, the limit as delta x approaches 0, is called a difference quotient. And there are a couple different ways you would say this. Some books use an h. They use f of x plus h minus f of x over an h, and take the limit as h approaches 0. Those are the two most common quotient, or difference quotients to find the derivative. Now we're going to do a problem, walk you through a problem where you find the derivative using this limit definition. Not yet. We're going to give you the notation for derivatives, then we're going to do a problem. Some of the notations for the derivative. If you're given a function, the derivative is notated as f prime of x, little apostrophe between the f and the parentheses. Dread f prime of x. Another notation is dy dx, a dy over a dx. These are called differentials. This is read the derivative of y with respect to x. So if you were given an equation y equals 7x squared plus 2 or something, dy dx would be the derivative of that equation. Or they might write it, if you're in y equals form, y prime. Again, y with a little apostrophe. These are the three most common notations for derivative. Two other notations for derivative will be the derivative with respect to x. We're deriving in terms of x, and then you have brackets and your function, whatever that was, 5x squared plus 4x minus 11, or whatever. So you have derivative with respect to x, and then in brackets your function that you're deriving or you're differentiating. That's somewhat common, not as common as these three, but you will see it from time to time. This isn't as common, but you will see it sometimes, it's a little more rare, but it's good to know, just in case you ever see it so you know you're familiar with the notation. Capital D with a little x, a sub x, and then your brackets, and again your y, whatever it is, y equals 4x cubed minus 11, something like that. So these were the notations for the derivative. Again, the most common ones you'll see all the time, a fairly common one, and a relatively rare one, but still used and still important to know, to be familiar with. The derivative itself, it's important to think of the derivative in a few different ways. The slope of the tangent line is the most common way. The derivative is the slope of the tangent line at that point. It's also the slope of the graph of the function at that point. So a problem might say, find the slope of the graph at x equals 7. All they're asking for is the value of the derivative at x equals 7. And finally, it's the instantaneous rate of change. If you're given some kind of vertical motion problem, you have a falling object, and they say how fast is the object falling at 7 seconds, well, they want to know what's the derivative of the function, what's the value of the derivative of the function at 7 seconds. Now here's an example where we're going to use that difference quotient, that limit definition of a derivative, to find the value of the derivative. We start with the function f of x equals x squared minus x. We know that the derivative f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. That same difference quotient we did a couple slides back. Now we're going to use some algebra at this point. Once you know this is a derivative, the rest of this, all the way to your answer, is just algebra. Goes back to your Algebra 1 course. F of x plus delta x. I take x plus delta x, put it in anywhere I see an x. So I get x plus delta x squared minus x plus delta x. This squared minus this. X squared minus x. That's f of x plus delta x. Be careful. It's important you put the original function in parentheses so this negative sign goes through and you don't have any sign errors when you go to simplify next step. All over delta x. So again, x plus delta x goes in for every x term. X squared minus x minus the original function all over your delta x. Still, the limit as delta x goes to 0. If I plug in, just real quick, if you plug in 0 here, direct substitution, f of x plus 0 is f of x, minus f of x goes to 0 over 0. You have your determinant form, so that's why we have to go through this. That's why we have to simplify this in order to be able to use direct substitution to get something that would be equivalent. Next, I square this out. X squared plus 2x delta x plus delta x squared. Binomial squared gets you this trinomial. Minus x minus delta x. Send that negative sign through. Then send this negative sign through. Minus x squared plus delta x. I'm sorry, plus x. All over delta x. So we got rid of the parentheses and sent the negative signs through. Now, as you see here, and this will always happen with the limit definition of the derivative, things will cancel. X squared minus x squared, those two go. Minus x plus x, those go. I'm left with 2x delta x squared, and a minus delta x as my numerator. The x squared and the x both canceled out all over delta x. Come over here. There's what you're left with. Have a delta x in this term, delta x in this term, delta x in this term. You want to factor out a delta x. So you have the delta x times 2x plus delta x minus 1 all over delta x. Now this is nice because this is where we can cancel a delta x and we'll no longer have to worry about direct substitution giving us an indeterminate form. Delta x is canceled, so you're left with 2x plus delta x minus 1. Now we can use direct substitution. Delta x goes to 0. The limit as delta x goes to 0. 2x plus 0 minus 1. So our derivative, the limit as delta x goes to 0 of the difference quotient using this original function, f prime of x is equal to 2x minus 1. So the slope of the tangent line of this function at any value of x is equal to 2 times the x value minus 1. So we'll look at a picture of this next and some specific values. Our original function, x squared minus x, you see the graph down here, a quadratic, a parabola. The derivative we found on the last page was 2x minus 1. I've picked 2 points, 0 and 2. X equals 0 and x equals 2 on the graph. 0, 0, 2, 2 are points on the curve. So to find values on the curve, you go to the original function. To find the slope of the tangent line at those points, you go to the derivative. F prime of 0, the derivative at 0 is negative 1. 0 minus 1 is negative 1. So the slope of the tangent line, if I draw a tangent line here, should be negative 1. You can see the tangent line is going down, and it's not going down too steep, so negative 1, with a little eye test here, makes sense. Slope of the tangent line at 2, f prime of 2 equals 3. 2 times 2 is 4, minus 1 is 3, meaning if you drew a tangent line at x equals 2, somewhere in there, you should have a slope of 3. Down here you have a slope of negative 1. Over here it's a much steeper slope, even though it's going vertical or going positive, it's still definitely a steeper line. So it makes sense that that's more than this, and 3 does make sense again with an eye test. So to find the value of the slope of the tangent line at any point, you find the derivative and you plug in the x value to find what the slope of that tangent line would be. Just like limits could not exist, since the definition of a derivative comes from the limits, we can also have derivatives that don't exist. if a function has a derivative that does not exist at a point, the function is said to be not differentiable at that point. There are three ways a function cannot be differentiable, or where the derivative does not exist. The first is the function is not continuous at that point. If the function is not continuous, then it does not have a derivative at that point. It could have a derivative at other points, but not at the point where it's not continuous. The second way is if there is a sharp turn in the graph. Most closely associated with absolute value graphs, where you have your point where it switches from positive to negative, or negative to positive depending on the orientation. So at this point right here, where the absolute value graph comes to a point, that function is said to be not differentiable at that point only. It has a derivative everywhere else, excuse me, but the derivative at that sharp turn does not exist. This can also happen if you have certain root functions, certain radical functions, where you might have something where it's hooking in from this side and then coming to a point and hooking out from that side. Certain radical functions also look like that. Those are the most common types of functions where you have a derivative that fails to exist at a point because of the sharp turn. And finally, if the function has a vertical tangent line at the point. The slope of a vertical line is undefined. Since the derivative is the slope of the tangent line, if the tangent line is vertical, the derivative is also undefined. So here's a cube root function where you're going to the right, you're coming up, you have a vertical tangent in here, and you turn back down. So the function is differentiable everywhere, except it looks like x equals 3 right here. So it's not, it can be differentiable everywhere but at a point. Doesn't mean you can't find the derivative anywhere. It means you can't find the derivative at that point of your vertical tangent line or of your sharp turn in the graph. An alternate definition of a derivative. Sometimes you can find the derivative or use a specific point to find the derivative. If you want to find the derivative at the point x equals 3, well, you can find f prime of 3, since you know that's where you want to find your derivative, by taking the limit as x approaches that value. Meaning as x value gets closer and closer to that number, well, if you were taking secant lines and the x's got closer and closer together, you would be doing essentially the same thing. The value of the function, the value of the function at x minus the value of the function at c over x minus c, whatever that constant is. Same idea. The limit as those two numbers, those x values, get closer and closer together. As you take your slope of your secant lines, difference of the y's over difference of the x's. In order for this alternate form to exist, the derivative from the left must equal the derivative from the right. Just like limits, and left-handed limits and right-handed limits, derivatives have the same thing. You can find a left-sided derivative, or a left-handed derivative, or a derivative from the left or from the negative, as you can find a derivative from the right by taking values from the right as you're coming closer and closer to C from the right. So if here's your point C, from the right side and becoming closer and closer like this, or from the left side and becoming closer and closer like that. And finally, just a little bit of a theorem here. Differentiability implies continuity. Meaning, if a function is differentiable, if it has a derivative at that point, then it must be continuous at that point. Excuse me. The reverse is not true. Just because a function is continuous does not mean it's differentiable. It can be, but it doesn't have to be. For example, if you had a sharp turn in the graph or a vertical tangent line, even though the function is continuous at that point, it is not differentiable at that point. But if a function is differentiable, it has to be continuous at that point.